Good morning, students. Today we'll discuss some examples of bounded linear operators and continuous operator. So, the first example of bounded linear operator is identity operator. Let us take a norm space X and define an operator I from X into X, defined by I of X is equal to X. This operator is called identity operator, that is a linear operator. And if we find the norm of this operator, by definition, norm of I, this is defined by the supremum of norm of Ix divided by X norm, where this supremum is taken over all the non-zero elements of the domain of T. Now, I of X, that is X, so this will become supremum of norm of X divided by norm of X. So this will become 1. So norm of the identity operator, that is 1. So this is the first example of bounded linear operator. Next example is zero operator. Let us take norm spaces X and Y and define an operator from the norm space X into the norm space Y by 0 of X is equal to 0 for every X belonging to X. Now, this operator, that is a linear operator defined on X, and also the norm of this operator, that is 0. This operator is also a bounded operator. Next example is differentiation operator. Let us take a norm space X be the space of all the polynomials defined on the closed interval 0, 1 with the norm of X defined by the maximum of mod of X. Here X is the function of T and T belongs to the closed interval 0, 1. We will show that a differentiation operator defined on this norm space X defined by T of xt is equal to X dash T. This is linear operator but not bounded. So first of all, let us prove that T is linear operator. To prove this, let us take two elements X and Y from the norm space X and two scalars alpha and beta. Now let us find the image of alpha X plus beta Y under T. Now by definition of operator T operated on X, that is given by the derivative of X. So the image of alpha X plus beta Y under T, that is given by the derivative of alpha X plus beta Y. Alpha and beta are scalars, so this will become alpha into derivative of X plus beta into derivative of Y. Now X dash T, that is image of X under T, and Y dash T, that is image of Y under T. So this becomes alpha into image of X plus beta into image of Y. So this proves that T is a linear operator. Now we will show that this operator defined on X, that is not bounded. So in order to show this, let us take a natural number n and we define xn is equal to t raised to the power n. Here t belongs to the closed interval 0, 1. Now let us find the norm of xn. By definition of norm, we have defined norm of x is equal to the maximum of mod of xt, where t belongs to the closed interval 0, 1. So using this definition of norm, let us find the norm of xn. This will become maximum of mod of xn, where t belongs to the closed interval 0, 1. Substituting the value of xn here, the value of xn is t raised to the power n. So this will become maximum of mod of t raised to the power n, where t belongs to the closed interval 0, 1. Now on this interval, the maximum value of this, that is 1. So norm of xn is 1. Now let us find image of xn under t. By definition of operator t, this will become the derivative of xn, which is denoted by xn dash. Now the derivative of xn with respect to t, xn is t raised to the power n, so its derivative will be n into t raised to the power n minus 1. Now let us find its norm, norm of image of xn. By definition of the norm, this will be maximum of mod of xn dash. Now substituting the value of xn dash, this is n into t raised to the power n minus 1. Now this maximum value, that is n. Now because n is a natural number which is arbitrary, so we can say that there is no fixed number c such that t of xn norm divided by xn norm is less than or equal to c. So we can say that the operator t, that is not bounded. So differentiation operator is an example of linear operator which is not bounded. Now next there is a theorem which states that if a normed space X is finite dimensional, then every linear operator T defined on X is bounded. So let us take the normed space X is finite dimensional. So let us take its dimension is denoted by n. Because its dimension is n, it means its basis will consist of n vectors. So let us take the set e1, e2, e3 up to en. This be the basis for the normed space X. Now by definition of basis, every element of X can be written as a linear combination of these vectors uniquely. So for X belonging to X, we have a unique representation of the form of the linear combination of these vectors. So let us take X is equal to summation exile I ei. Here I varies from 1 to n, and these exile i's, these are the scalars. Now we are to prove that T is bounded linear operator. By definition of bounded, it means we are to prove that Tx norm is less than or equal to C times norm of X, where this X belongs to the normed space X. So let us consider the norm of Tx. Now substituting the value of X, which is summation exile I ei. Now because T is linear operator, so by linearity of T of this vector, that will be summation exile I T of ei. Now we can use triangle inequality in norms. So by that inequality, this will be less than or equal to summation norm exile I T of ei. Now by using absolute homogeneous property of norms, this will be further is equal to mod of exile I into norm of T of ei. So finally T of X norm is less than or equal to maximum of norm of T of ei into summation mod of exile I. Now to find its value, we will use lemma, which we already discussed, linear combinations lemma. According to that lemma, if we have a linearly independent set of vectors x1, x2, x3 up to xn in a normed space X, then there exists a positive number C such that for every choice of scalars alpha 1, alpha 2, alpha 3 up to alpha n, we have the norm of the linear combination alpha 1 x1 plus alpha 2 x2 and so on alpha n xn, that is greater than or equal to C times the sum of absolute values of the scalars alpha i's. Now using this lemma here, we can find the value of summation mod of exile I. So by this lemma, C times the sum of the absolute values of exile i's, that is less than or equal to the norm of the linear combination exile 1 E1 plus exile 2 E2 and so on exile n En. So from here, because C is non-zero positive number, so we can divide third by C. This will become summation exile I mod is less than or equal to norm of exile 1 E1 plus exile 2 E2 and so on exile n En or divided by C. So substituting this value here, this will become norm of Tx is less than or equal to maximum of norm of T of Ei's into norm of exile 1 E1 plus exile 2 E2 and so on exile n En divided by C. Now this is x, so this will become norm of x divided by C, and this term we have taken as it is. Now we can write this value as C dash. So we have obtained T of x norm is less than or equal to C dash into norm of x. So by definition, we can say that T of x norm is less than or equal to C dash into x norm for every x belonging to the norm space X. And by definition, this proves that T is bounded. Thus, we have proved that every linear operator on a finite dimensional norm space that is bounded.